Hello everyone, my name is Ibrahim. This is Juan, Tyler, Jay, and Greg. We are working on Hawthorne native RAM improvements, and we're a SaaS group. Here is an outline of our presentation for today. We're going to go over background, existing site condition, alternative analysis, facility design, modeling and theoretical calculation and conclusion. Here is the project site. It's located on Hawthorne Bridge at the west approach. So this is the intersection where the where northbound NATO RAM merges with southwest Madison Street when entering the Hawthorne Bridge. The stakeholders of this project are Multnomah County, Peabody, and Twilight. The Hawthorne Bridge serves around 10,000 cyclists a day, 10,000 cyclists and commuters a day in the summertime. The Hawthorne Bridge is a bike-friendly bridge. Peabody plan for 2030 is to make more than 25% of all trips in Portland to be made by bicycle. Here is the existing site. I'm going to explain some conflict areas in this intersection. The first conflict area is the bicycle and vehicle. Here we have cyclists entering from southwest Madison Street, and here we have vehicles coming from northbound NATO, encroaching the crossing bicycle lane of Madison Street, making it unsafe for cyclists, and that caused near misses. This conflict area impedes the flow of vehicle traffic from NATO Parkway. As a result, during the peak hours, a long queue forms extending over half of a mile down NATO Parkway, blocking first the C-car at southwest Madison Street and the MAX at southwest Jefferson Street. The second conflict involves a bicycle. Here we have cyclists entering from NATO ramp, and here we have cyclists coming from Madison merging on this spot. So that will cause near misses. The third conflict involves a pedestrian and bicycle. Here we have pedestrian coming from southwest Madison Street, entering the bike lane from NATO ramp, and that caused near misses. And now I will move it to Juan to talk about the alternative analysis.
So after consulting with our client and meeting with the Multnomah County Pedestrian and Bike Committee, we have considered 4 alternatives. The first alternative is closing the ramp for vehicles. So the ramp is going to be accessible for pedestrian and cyclists, and vehicles coming from the NATO Parkway will take southwest Jefferson Street, and they will be rotating into southwest 2nd Avenue and turn right in southwest Madison Street. This alternative will provide a smooth traffic flow from southwest Madison Street into the Hawthorne Bridge. However, the main issue with this alternative is it's going to increase the conflict between vehicles and pedestrians in these intersections. The second alternative that we consider is to signalize the intersection. We're going to place the first signal here. We're going to stop vehicles coming from north from the NATO Parkway, and the second signal is going to be placed here. It's going to stop vehicles and pedestrians and cyclists. The third alternative is similar to the second one. However, instead of signalizing the two lanes, we're going to signalize the right lane, and the left lane will be going, since it's not interfering with vehicles coming from the NATO Parkway. And the last alternative is the no-build option, and we're going to keep the site as is. We've considered different criteria. The first one is safety. It's going to evaluate the safety of pedestrian and cyclists. And the second criteria is cost. We're going to evaluate how much the project is going to cost, associated with construction material and labors. And we have the non-conjunction. We're going to see how the design is going to improve the traffic flow and the nature ramp. And we have maintenance. We're going to evaluate how to maintain the project in the future. And the last criteria, we have the cyclist approval. We're going to evaluate the feedback from the Multnomah County Pedestrian and Bike Committee. These criteria have different weights based on how are they important to our client. So we have safety, cost, and road conjunction are weighted high. However, we have maintenance have the lowest weight. We use the Pew matrix to start alternative analysis. As you can see here, in safety, cost, and ramp have the maximum score, 15 out of 15, and we have the maintenance 5, and cyclist approval 10, which give us a score summation of 60. Here we have the alternative analysis that we performed, and each alternative have their score. As we can see here, the two signal have the highest score. So as a group, we decided to choose this alternative as the preferred alternative. And I'm going to hand it to Tyler to talk about the facility design.
So I'm going to discuss our design aspects, specifications, and guidelines for this project. For our first signal, we referenced the design manual by ODOT for signal design. We're going to construct a steel mast arm. The pole length is going to be 20.5 feet, and the mast arm is going to be 19.5 feet from the base of the pole up. On the mast arm, we're going to have attached 2 Type 2 standard traffic signals, and these will be centered in the lanes. This will meet the specifications on both height from signal head to roadway and in distance between each other for signal heads of the same phase. Also, the pole will be constructed 2 feet from the curb. The foundation for the pole will be 1.5 feet in depth and filled with commercial grade concrete. The rebar will be number 8 vertical spaced around the perimeter, and we will use 4 hoops of length 3 feet, and these will be spaced 6 inches apart along the circumference. The base plate here will be at the top, and this will attach the pole and the foundation together. The base plate is going to be 1.5 feet in diameter, and we're going to have 4 anchor bolts that are going to bolt down the mast arm. So our next signal is my favorite signal, because this is the lollipop design signal, as I like to call it, and it is just going to be a steel pole with the same foundation as our last pole in depth and width. It will also have a Type 2 signal head, and ooh lolly lolly, it's going to have some pedestrian signals on it and that is going to correspond with a pedestrian signal that is going to be on our mast arm. We decided to combine the cyclists and pedestrians together when crossing the NATO ramp. We thought this would be safer and they'd be more visible to vehiclists on the ramp. So our temporary traffic control, both eastbound lanes are going to be closed on the Hawthorne during the construction, and so vehiclists Vehiclists on Madison are going to turn left onto 2nd and go up and then cross over the Morrison Bridge. Vehiclists on the NATO Parkway are going to travel north, cross the Morrison Bridge, and then both, if they need to head south, will go down south on 7th. All this can be avoided if Aaron can just convince his clients to build a new bridge. And so up next, Jay will do theoretical calculation for us.
For signal installation, I would like to talk about how we approach this problem to calculate our signal timing. So we referred highway safety manual with 7 steps. Step 1, phase analysis. 2, geometry, saturation flow rate, flow ratio, critical lane groups, minimum optimal cycle length, green times, yellow and or red times. Before we calculate our signal timing, we obtained our traffic volume data from location 1 here, which is the intersection between the Madison and the 1st Avenue. And then we also collected our traffic volume data on location 2 from NATO Parkway approaching to Hawthorne Bridge. So here's the data table we got from City of Portland. So for location 1, since the southwest 1st Avenue was the one-way street, we take the traffic volume of vehicle which take the left turn here, and then we also took the traffic volume for southwest Madison Street, and then we made summation of those traffic volumes. For location 2, we only measured traffic volume approaching to the Hawthorne Bridge, which is right here. So for the first step, we divide by 2 phases to calculate our signal timing. And then we input our geometry data. So since we have 2 phases, our total rose time was 8 seconds, 4 seconds for each phases. And we input our speed limit on the side and then width of the cross street. After that, we input our saturation flow rate. Saturation flow rate is measured when we have signal, but since we don't have signal yet on the side, we had to assume. So in order to get the optimal saturation flow rate, we referred Bistro, and we got the number right there. After that, we calculated our flow ratio, which is peak hour volume divided by saturation flow rate, and then we made summation of flow ratio to calculate the next step. Here's the minimum and optimal cycle length here. And then we calculated critical ratio for the intersection. After that, we calculated our green time. Everything has been performed with Excel spreadsheet, so we were able to put our different traffic volume and different saturation flow rates as we assumed, so we can easily calculate without making any changes. So we were able to verify our number is okay because green time for both phases, summation of those and then total rose time matches with our cycle length. After that, we calculated our yellow and red time. For this calculation, we used a lot of human factors, for example, driver's reaction time, speed of vehicle, deceleration or acceleration, percent grade, divided by 100. For those numbers, we only used standard numbers to get the standard signal timing.
What was that again?
Since we got our minimum cycle length and optimal cycle length, we calculated to see how the signal timing changes depending on the cycle length. However, our theoretical calculation method had some limitation because those cycle length doesn't care, does not take account to the other intersection, or it doesn't account any bicycle or pedestrian volumes, and then it was difficult to simulate if that works or not. So with our calculated signal timing, we simulated with modeling program, which is Bistro. So now Greg is going to talk about how the modeling program works.
Okay. Are you guys laughing? Modeling is an essential element to signal design and network optimization. For this project, we used Bistro. It provides signal optimization for individual intersections as well as networks of intersections. It optimizes signal timing by balancing the volume to capacity ratio. This is the network that I built to optimize our new signal, and the red arrow shows where the ramp is. The first step of modeling is to build an existing intersection. As you can see, there's a single stop sign controlling the intersection. During the peak hour, there's 404 vehicles entering from NATO and 1,638 entering from Madison Street. After building the surrounding network and inputting the volumes, Bistro calculates the level of service and other indicators based on the highway capacity manual. The level of service from the NATO approach is F, and the 95th percentile Q length is 1,257 feet. The Madison Street approach is uncontrolled, and therefore the approach level of service is an A, and the 95th percentile Q length is 0. So does this intersection justify a signal installation? A warrant is a condition that an intersection must meet to justify a signal installation. The manual on uniform traffic control devices specifies 8 warrants. The report generated from Bistro indicates that this intersection meets the first 3 warrants. So a signal is justified. After analyzing the existing intersection, I modified the network to represent the proposed alternative. This is the signalized intersection. The optimized signal group splits given by Bistro, 31 seconds for the NATO approach and 59 seconds for the Madison Street approach. The intersection level of service is now a C. It also must be noted that the approach level of service from Madison Street is no longer an A because it's now signalized. By signalizing this intersection, the 95th percentile Q length of the NATO ramp drops from 1,257 feet to 366 feet, and the intersection level of service increases from an F to a C. PTV VSIM is a simulation software where I can insert a network that was designed in Bistro to create a 3D animation. This is the existing intersection. As you can see, pedestrians and traffic flow from Madison prevent cars from NATO to enter the bridge. This is the signalized intersection. Currently, vehicles, cyclists, and pedestrians from Madison Street have a green light, while the ramp from NATO has a red light. The signal is coordinated with a signal at First and Madison that's 480 feet away, and the offset is 11 seconds. Now the signal has changed, so vehicles along with pedestrians and cyclists from Madison have to stop, allowing vehicles from NATO to flow freely onto the bridge. This is a simulation of the entire network with the proposed signal installation. As you can see, it no longer causes a queue to form on NATO. So the next steps for this project would be to collect more accurate and up-to-date traffic volume counts. The ones we got from the city of Portland were a few years old. Another step is to consider the structural elements of adding a new light to the bridge. We'd like to acknowledge Megan Neal and Mark Haynes, Chris Moon's here, and Evan Christoph. Thanks for showing up, guys. Any questions?
Is the light going NATO northbound, is that a restricted red or permissive red to the right turn?
It's a single lane, so it's not permissive, it's protected.
When you're in the red,
No turn on red? Yeah. Any other questions?
Again, does the signal influence pedestrian or bike traffic from NATO?
Yeah.
Or it does, so it stops all that?
Anything else?
What's the duration of the signal?
9 seconds.
90 seconds?
It has to be the same as the intersection at First and Madison. To coordinate cycles, they have to be the same cycle length.
Why didn't you only signal just the right lane? Because isn't the middle lane just keep going over the bridge with that guardrail in the middle, so it's not like anybody could switch lanes anyways?
The light that we're proposing to install is before that median is there. And we want to signalize both lanes so that we don't have cars trying to move back and forth right in front of the median.
Yeah, one of our alternatives was to put a median there, but then we were worried about safety because people would either altogether avoid the right lane because they don't want to get a stoplight, and so we'd have cars flipping over to the left lane and then flipping over back, and then it was just not safe.
Okay.